because I have some animations, I have to use my mouse.
Okay.
Yeah, the goals, for example, one of the motivation of our work is to develop lightweight metallic structures with improved damage tolerance behavior. And one of the application case is the aeronautical industry, where we have the greatest challenges to achieve the lightweight design. One of the challenges to implement sustainable aviation, and there are some goals to reduce emissions, and it means that 75% of the world fleet has to be replaced by new, where we have to implement new designs for propulsion systems and airframe structures, and it can be done if we use innovative materials with a higher strength, lower density, and innovative processing technologies such as laser-based techniques for joining, additive manufacturing, and residual stress engineering. And exactly the laser processing of metallic materials is the focus of activities of my department. The process of laser shock cleaning was already explained. Here is only one motivation using our experimental facility. We have high energy laser, and here is, for example, the treatment of thin metallic waste. And the process can be effectively used for retardation of particular growth or retardation of operation of direct initiation. Next slide. And we have also investigating another process with a defocused laser beam. We can introduce local plastic yielding on the plate, and in opposite to laser shock pinning, where the laser heating, it's the name of the process, was applied. We have tensile residual stresses which are in balance with compressive residual stresses outside. And idea is to apply these processes for retardation of fatigue growth, and if every manufacturing process has to be applied for industrial applications, we need reliable modeling approaches to predict the effect of the processes, to understand how we can optimize the processes, and to understand how we can implement and optimize residual stress design. And with regard to modeling approaches, there's in principle different modeling approaches exist. One classical way, for example, for laser heating is to perform, first of all, thermomechanical analysis to calculate residual stresses. Then you can introduce residual stresses in the fracture mechanical analysis. You can calculate stress intensity factors and use empirical equation to predict fatigue crack growth. For laser shock pinning, a similar approach can be also implemented. However, we have to first of all to perform laser pinning process simulation, for example, using the Johnson-Cook model. Then we can introduce residual stresses in the finite element model, then a similar fracture mechanical analysis and prediction of fatigue growth. There are some papers where this approach was successfully implemented. Please continue. However, engineers working for aeronautical industry are interested to use commercial software such as AvGrow or NASGrow, where analytical approaches are implemented for including the effect of residual stresses. In such software, typically residual stresses are accounted using the wide function methods. And there are some publications where it was investigated if we model the fatigue growth of a specimen with residual stresses introduced, for example, using laser shock pinning process. And if you see here are some disagreement. And if you continue, and therefore the motivation for the current study was to investigate whether we can successfully model fatigue growth using wide function model, wide function approach, and as application cases, we investigated both processes, laser heating and laser shock peening. Can you continue? The concept is in principle simple. If in linear elastic fracture mechanics, the white function can be interpreted as a green function in early approach for a stress intensity factor problem. If you know, for example, the residual stress profile, the specimen, using the integration, we can calculate the stress intensity factor due to the presence of residual stresses. Continue. And there are some solutions exist, for example, for H crack with infinite lengths, we can use solution according to C. You can continue. For specimen with infinite width, we can another, and here for a CT 50 specimen, for example, according to Fed at moons, continue. And for central track, we can use, for example, simple green function, continue. If we can consider the finite width, we can use solution according to Dada and others. And for MT specimen, for example, their solution exists for Wu and Carlson. Okay, continue. And how to analytically predict fatigue crack growth. First of all, we can calculate stress intensity factor due to applied loading. Here are the solutions are shown for our cases CT50 and MT100 specimen. Continue. And if we know stress intensity factor, we can calculate fatigue crack growth using different equations. There exist, for example, Paris Walker equation. We can also consider the stress ratio, or NASGRO equation, where we are interested, where we can consider near threshold or near the fracture toughness behavior. And as we are interested only in the fatigue crack growth, we are tried to use the simplest Paris law for prediction. Continue. And the question is how to introduce residual stresses. We followed the approach proposed by the German engineer Elbar. Elbar considered that we can represent Paris law using the effective stress intensity factor in order to consider the crack closure effect. And here is his approach. And crack closure effect, we suggest there are similarities due to the presence of residual stresses. We can also introduce crack closure effect. And therefore, idea is we're using our Paris law with effective stress intensity factor and identifying the parameters of crack closure due to the presence of continuum. And how we can do it? We calculate the total stress intensity factor from minimum load and maximum load, considering the residual stresses, and stress ratio. In our case, if we're interested to have to calculate the effect of residual stresses, it's not equal to minimum divided to maximum load. It's our K dot divided to K dot max, considering the effect of residual stresses. And residual stress intensity factor due to the presence of residual stresses, we are calculating using the white function method. And if we have a situation that K mean less than 0, we just set to 0 in order to represent the hard surface contact. But this is the case in the reality. Please continue. And here are our application cases. Laser shock peening was applied double-sided on CT50 specimen, and we analyzed residual stresses due to using the high energy X-ray diffraction. Here are the maps of through thickness residual stresses. And for white function method, we are interested only in epsilon component. Here are the profiles, for example, for 2 cases are shown. Next slide. And here are the calculated solutions for applying the white function method for the stress intensity factor due to the presence of residual stresses. And as you can see here, we have only disagreement if we consider the solution where we do not consider the finite specimen width. For CT50 specimen geometry, it's important to use a solution where we consider the finite specimen width. Continue. And here are the results of prediction. Here is to show we can have only disagreement if we use a solution where we do not consider the finite specimen width, but in other cases we are in a very good agreement with the experimentally obtained results. Next slide. And for laser heating, we investigated empty specimen geometry and different application cases if we just apply laser heating lines or just circles in the front of the central track. Next slide. And here are the residual stress profiles determined also using the high energy X-ray diffraction for the cases with laser heating lines. Next slide. And here are the residual stress maps using the identified also using the X-ray synchrotron diffraction. And here are the profiles for the case if laser heating was applied as a circles. And as you can see, for some cases we also have the gradient in epsilon direction with regard to residual stresses. In principle, in the case of where we have circles. In the case of lines, we have more homogeneous residual stress profiles. Next slide. And here are the results of calculation of residual stress intensity factor due to the presence of residual stresses. Here you see we have already very good results applying the simplest green function. Next slide. And here are the results with regard to prediction of fatigue regrowth rate for specimen with lines and experimentally obtained results and results using the prediction. You see we are in a very good agreement, yes. And in case of circles, sometimes we have good agreement, for example, if the distance is a little bit far away, but if we have distance very close or multiple circles are applied, we have here disagreement. And the next slide, here are the results show the predicted crack length versus number of cycles. You see, especially for circles, where we have multiple circles or they are very close, we have disagreement. In other cases, we have very good agreement. And if I analyze how the crack propagates, in case of circles, you see that we have here out of plane crack deviation, multiple crack branching, and this is due to the fact that we have also gradient in epsilon direction. And of course, that kind of effects are not considered by the wide function method, and they have an additional contribution to the retardation of fatigue regrowth. So far, it has to be considered, not if we have such effects, wide function method cannot be applied. Next slide, and here is the summary of my talk. In principle, I have shown you that wide function method is a very powerful tool for predicting the fatigue regrowth rate in specimens with with induced residual stresses. And one important, of course, aspect, you have to consider the limitation of methods if we have additional retardation effect due to the non-straightforward propagating of the crack. For such cases, wide function method is not applicable. And the next slide, I would like to make your attention. Next year, the International Fatigue Congress will take place on the beautiful island of Madeira. And considering the very successful event in Melbourne in 2014, we are also interested to organize a symposium related to laser pinning and related residual stress processes for fatigue improvement, and together with my colleagues, Professor Yuji Sano from Japan and Domenico Furfari from Airbus Germany, we are organizing symposium. Welcome to submit abstracts. Here are the dates. And thank you very much for your attention. And it's a pleasure. I'm open for questions.
Thank you very much.